Today we're going to start section 11.5 and we're going to look at two main different types of probability problems. So we're going to look at OR problems and problems. Today we're just going to focus on the first type. We are going to be looking at OR problems. As we're going through this entire section, what we're thinking about and what we're looking at is something called compound probability. Compound probability problems contain the words and or. Right? When we're doing these and when we're thinking about our compound probability, it's kind of like the idea of a compound sentence. Right? A compound sentence, we often use a word like and to join them. So in this case, we're going to focus on the words and or. Right? Starting with or. Right? We're going to tie this back to some of the stuff that we just talked about in chapter 2. Right? In chapter 2, when we are thinking about the word or, right, we were thinking about unions. So as we're thinking about our OR probability problems, these are very similar to our union problems that we saw back in chapter 2. Right? So often we want to study more than one variable at a time. So the word OR can be used to combine our events into new, more complex events. The OR probability problem, right, is looking at obtaining a successful outcome for at least one of the given events. Right, so as we're doing these, again, we're thinking it could be on the left side, right, in event A, it could be on the right side in event B, or it could land in that middle part that's both. Right? So our OR probability is just like our OR Venn diagrams, where we want everybody that's included in here. As we're going through and doing these problems, the big thing that we want to watch out for is we want to make sure we don't accidentally count that middle group twice. As far as how we can eliminate counting that middle group twice in our formula, if we're using a formula, we can take our probability of event A plus our probability of event B and then subtract the probability of both. Right? This is going to eliminate the possibility of an event being counted twice. So we're going to go through these problems a few different ways. In some of these we're going to talk about Venn diagrams, and then in some of these we're actually going to use our formula. So again, we're going to tie a lot of what we saw in chapter 2 into these types of probability problems as well. Okay. So our first example here down at the bottom then, right, this Venn diagram shows information about 6 people. Suppose we select a person at random. What is the probability that the person is wearing a hat? And that's a typo. It should not say and, that should say or. Right? So again, we're thinking or probability. So on your document, you might want to change that, cross off the word and write the word or in there. All right, so thinking about our Venn diagram, well, that means we want anybody that's in here. Right? So hat or glasses means they could be wearing a hat, right, as in the left, glasses as on the right, or both as in the middle. Right? If we're looking at this, we have a total of 5 people in there. Notice that we do have one person outside, right, in our universal set. So our probability of a hat or glasses is going to be 5 out of 6. So or everybody that's inside our Venn diagram. Next couple of examples we're going to walk through using Venn diagrams as well. So in this next one, each of the numbers 1 through 10 are written on separate pieces of paper. The 10 pieces are then placed into a hat and 1 piece is randomly selected. Determine the probability that a piece of paper selected contains an even number or a number greater than 6. Right, so let's start with our even numbers. Right? And then we'll look at our numbers greater than 6. So if we label our Venn diagram, I'm going to label this side as even, and then I'm going to label this set over here as greater than 6, and I'm just going to use a greater than symbol there. So as we did in chapter 2, when we're filling these in, we want to start with the intersection. Right? So looking at these, the even numbers that are both greater than 6, we're going to have an 8 and we're going to have a 10. Right, so we're going to put these two numbers here in our middle because they are both numbers that are even and they are also greater than 6, so they are in that center portion. Our other even numbers that we have left over, well, we still have 2, 4, and 6, so they're going to go over there on that side. Our numbers that are greater than 6, we've already used 8 and 10, so we want to use 7 and 9. Right? And anything that's left over that we haven't used, we're going to put that outside in our universal set. So we're going to have a 1, a 3, and a 5 left over. Right, so on the previous page, we had a formula. And our formula said that the probability of A or B, right, is the probability of A plus the probability of B minus the probability of A and B. Right, so we're going to talk through this example in two different ways. So we're going to use our formula from the previous page, and we're also going to look at our Venn diagram. Right, so looking at our Venn diagram, we'll let event A be our probability that our number is even. Right? So if we look at these, and if we look at our Venn diagram total, right, we have 5 even numbers. 2, 4, 6, 8, and 10 are all even. So strictly using our formula, right, our probability of event A, if we let that be the even numbers, right, we have, that should be 5 out of 10. I don't know where the 8 came from. We have 5 out of 10 there. Right? Our probability of B is a probability of a number greater than 6. Well, the numbers that are greater than 6 are over here, but they also include 8 and 10. So we have 7, 8, 9, and 10. Right? So greater than 6 is going to be 4 numbers out of our 10. Now we're going to subtract the intersection, because what we've just done is we've counted this 8 and 10 twice. Okay? So we're going to subtract our number of numbers that are in the middle portion, which is 2 out of 10. So if we add these up and subtract them, right, so we have 5 out of 10 plus 4 out of 10 minus 2 out of 10. So 5 plus 4 gives us 9. 9 minus 2 gives us 7. And if we look at our picture, right, we have exactly 7 numbers that are in the middle here. So as you're working through and doing these problems, in some cases it might be easier to draw a Venn diagram, but if you do not have the option of drawing the Venn diagram, that's the other reason that we have this formula. Right? And the subtraction exists because we don't want to accidentally count those middle two, in this case our numbers 8 and 10, right, more than once. All right. So in this next example, example 3, we're going to think about the same 10 pieces of paper. Right? If one paper is selected, determine the probability that it contains a number less than 5 or a number greater than 8. So again, I'm going to label my Venn diagram. So we'll make that our less than 5 side, and we'll make this side our greater than 8 side. Okay. First, we want to fill in the intersection. Well, in this case, we don't have anything that falls in our intersection. It is impossible for a number to be both less than 5 and greater than 8 at the same time. So we're actually going to leave this middle part of our intersection empty. Right, so our numbers that are less than 5, we have 1, 2, 3, and 4. Our numbers that are greater than 8, we have 9 or 10. Right, our intersection is left empty, so that means anything else that we haven't used, we're going to put in our universal set outside. Right, so we haven't used 5, 6, 7, or 8, so we're going to put those in our universal set outside. So our probability of selecting a number less than 5 or greater than 8. Right. So instead of using A and B in this case, I'm just going to use our symbols. Right, so our probability of selecting a number less than 5, well, that's the numbers 1 through 4. So we have 4 out of 10. Our numbers that are greater than 8, well, we have 2 out of 10. We had 9 and 10 on that side. And then our intersection, well, there wasn't anything in our intersection. So 4 out of 10 plus 2 out of 10 gives us 6 out of 10, which then we can reduce to lowest terms to 3 out of 5. Again, if we look at our Venn diagram, we were thinking about the OR part, right? That was everything that was inside. We had 6 out of 10 numbers, right, inside these circle portions of our Venn diagram. Notice that if we compare our two examples, right, we have two different cases. We have a case where we do have something that's in the intersection, and we have a case where we don't have something that's in the intersection. That's what we're going to address in the next definition. Right. Mutually exclusive events is like our last example 3 that we just looked at. Events are called mutually exclusive when they have no outcomes in common. Right? So it's impossible to be both at once. Right? What this does is it gives us a way to shorten our formula if we have events that are mutually exclusive. Again, tying this back to our set theory that we talked about in the last chapter, right? Mutually exclusive events can also be thought of events that are disjoint. Right? It's impossible to be both. You're either in set A or set B, but there is no overlap. Right? Their intersection is the empty set. Right? These are disjoint sets. Disjoint and mutually exclusive mean the same thing. What happens to our rule then is instead of taking our probability of A plus our probability of B and having to do a subtraction, well, we no longer have to do the subtraction part because they don't overlap. So because there is no intersection, because our probability of both happening at the same time is 0, notice that our formula becomes shortened. There's nothing to subtract. Again, this is only true, right, for mutually exclusive events. Again, so mutually exclusive events, we're thinking about events that are disjoint. Right, so down at the bottom here, we have our nice picture of our deck of playing cards that we've used, that we're going to use as we're going through our problems. It's a little hard to see because this is not printed in color, but as we're looking at this, our first row up top, right, these are our spades, right, these are our black cards. And then the third row, our clubs, are also our black cards. Right? And then our hearts and our diamonds are the red cards that we have. Right? So we're going to refer back to this deck of cards as we're going through the next few examples. So I'm just going to move this out of the way for right now. So we want to determine whether the following pairs of events are mutually exclusive and then find our probability of A or B. Right, so our first example, right, we are looking at the probability of A being that we draw a card that is an ace. Our event B is the probability that we draw a card that is a jack. Right, so looking at our table here, right, our aces are over here on the left. Our jacks are over here, and if we look at that, right, there is no overlap. So in this case, our events are going to be mutually exclusive. Right? So they're mutually exclusive. Again, we can think about it as our sets being disjoint, or it is impossible to be both. Okay. So if we are mutually exclusive then, for our formula, right, we can use our probability of A or B is simply our probability of A plus our probability of B. Right, there's nothing to subtract because there is no overlap. Right, so our probability of A is the number of aces that we have. Well, if we look back to our picture, we have exactly 4 aces, so we have 4 over 52. Right. Our probability of jacks, we also have 4 jacks, so that is also 4 out of 52. Right? We add these guys together, we get 8 out of 52, which then would reduce to a fraction in lowest terms of 2 over 13. So a card being both an ace and a jack at the same time, right, is impossible. So these are mutually exclusive. So for B, we're asked about selecting one card, right? And we want to decide if being an ace and a heart are mutually exclusive or not, and then how we want to find our probabilities. Right? So if we look at our deck of cards, our aces are here, and then our hearts are along here. Notice that we do have a card that is both, right? We do have an ace of hearts. So in this case, when we do these, right, these are not mutually exclusive. Right? So for B, we are not mutually exclusive. So in this case, our probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B. Right? We have to do a subtraction because there is at least one thing that is both. Right, so our probability of drawing an ace. Right? Well, we just said we have 4 out of 52 cards that were aces. Right? Our probability of drawing a heart, we have 13 out of 52 cards that are hearts. Right? And we have exactly one that is both. Right? We have one ace of hearts. So 4 plus 13 gives us 17, minus 1 gives us 16 over 52, which then if we divide them both by 4, we get 4 over 13 as a reduced fraction. So the big difference between A and B, whether or not it's possible to be both at the same time. Right? If it's impossible to be both, as in A, they're mutually exclusive, no subtraction is required. If we do have at least one that's both, right, then we're going with B, or thinking about example B, we have to do a subtraction of what is both. Right. So let's work through a couple more. So for C, we're asked to find the probability of a red card or a black card. Well, in this case, right, we know looking at our picture that these are also mutually exclusive. Right? It's impossible to both be red and black at the same time. Right? So our probability of A or B is simply going to be the sum of our probabilities. Right? No subtraction required because these are, should be a P, mutually exclusive events. So our probability of A, well, we have 26 red cards out of 52. For B, we have 26 out of 52 black cards. That gives us 52 out of 52, which gives us 1. So our probability of drawing a red card or a black card is 100%, right? Because those are our only two options. Our red cards and black cards are disjoint sets. And then if we add them up, we actually get our universal set, which is our entire deck of cards. All right, for our last example then, we want to think about picture cards and red cards. In this case, it is possible to be both. So these are not mutually exclusive. So when we find our probability for this one, right, we're going to take our probability of A plus our probability of B minus our probability of A and B. All right, so A is going to be the probability that we draw a picture card. So I'm going to flip back to our diagram here for just a minute. If we look at our picture cards, again, face cards are only the ones that have faces on them. Right? So we have 3 of each suit for 12 total. Right? So our probability of drawing a picture card is going to be 12 out of 52. Our probability of drawing a red card, we have 26 out of 52. Right? And then we have to subtract the number of red face cards or picture cards that we have. So if we look at this, we have 1, 2, 3, 4, 5, 6 red face cards. So then we're going to subtract 6 out of 52. Right, so if we add these, 12 plus 26 gives us 38, minus 6 gives us 32 out of 52. If we divide these both by 4, then we get a simplified fraction of 8 over 13. So as we're thinking about our compound probabilities, what we've just looked at is we've looked at examples of OR probabilities. And as we're looking at the OR, again, one thing we have to consider and keep in mind is whether or not our events are mutually exclusive.